Hi, this is Dan Bowen, your friendly neighborhood stratospheric balloon expert. Let's continue our informal exploration of interesting balloon science papers. This is going to be part 3 of one of my favorite papers, Controlled Altitude Free Balloons. This paper is from 1947. If you're enjoying these videos, please like, subscribe, and share. So, one thing that I noticed in the prior 2 sections was that we were going through things in a rather sequential fashion, and that's not really how I like to get a first glance at balloon papers. Let's go ahead and take a glance through this entire document and pay special attention to just some simple things that may catch our eye. As we can see, the title, the abstract, we've gone over these in previous videos. Let's keep going past where we stopped reading. We stopped right before section 3 here, and we see in the next section that there is a pretty quarter-filled balloon, a polyethylene 20-foot diameter. That looks interesting. I'm not really going to explain things as we come through them at this point. This is really just to give you a little bit of a preview of things that might look interesting to you. It looks pretty cool. I like these old technical line drawings. Also, another cool line drawing. And here's another one. A mercury pressure switch. Looks like an electrical apparatus. A chart. This is a nicely drawn one too. A lot of these old science papers have been photocopied several times, and the graphs and charts are almost illegible. Another chart. Height time curve of balloon flight 17. So it looks like this is an actual flight record. Wind vectors. This is more flight records. That's less technically interesting. Height distance curve and planned trajectory of balloon flight number 11. All right, another flight record released at Alamogordo, New Mexico. Interesting combination of chart data here. We'll have to look at that later. And looks like another similar chart from a different flight. And that's the end. Cool. All right, let's go back to where we left off. Here we go. So the Japanese example showed that an envelope that would not stretch was the solution to flying for a long time. So a perfectly non-extensible balloon could be built with no diffusion. Remember, diffusion is basically a gas soaking through a material and could withstand high pressure. It would automatically stay at a constant density where the buoyancy of the full balloon equaled the load. This is exactly the same way fish and submarines will be able to float at a constant depth in the water. In practice, control devices are needed to offset the leakage and diffusion of gas, to compensate for the vertical currents, to correct for the motion of the balloon due to diurnal changes of the balloon's temperature, and to compensate for the valving of gas necessary to prevent rupture of the envelope. Well, that's a lot of things that they are preparing to compensate for. Interesting. Motion of the balloon due to diurnal changes of the balloon's temperature. That just means that it is possible that the balloon may cool down at sunset or heat down at sunrise. And at sunset, if the balloon cooled down enough for it to actually start shrinking, it would start falling. And at sunrise, if it was still shrunken a bit, the temperature would go up, which would increase the pressure due to the ideal gas law and cause it to rise up again. Decided to use a plastic as the balloon fabric. They're quite transparent to radiation, strong, easily fabricated. So transparent to radiation is important for protecting against the thing I just talked about, which is heating up in the morning and cooling down in the afternoon. And plastics are apparently inexpensive compared to coated fabrics of the time in 1947. Let's see, choice of plastics. So what you want to have for a balloon, a low brittleness temperature. That means the temperature at which the plastic starts to crack when you bend it. Low permeability, that's the diffusion through the film. High tensile strength, because the thing has to be pressurized. It has to be strong. High tear resistance. That's an obscure property we'll talk about later. Chemical stability. I'm assuming that means that the thing doesn't melt. High radiation transmission or reflection. And this is the same thermal thing we talked about. Polyethylene soon recommended itself for use with its brittle temperature of below -80 Fahrenheit. That is something that remains true today. Polyethylene is one of the lowest temperature, brittle temperature plastics available. Well, there are other special formulations that allow other types to get fairly low. Polyethylene just naturally has a very low brittle temperature. And their conclusion was it's apparently unaffected by ultraviolet and ozone. That's incorrect, but it's pretty darn good. So the permeability through 1 mil of thickness. So in these old papers, the imperial system of measuring thickness of very small dimensions often referred to things in mils. That's MIL. This actually refers to the quantity of 1/1000th of an inch. That's very confusing because it does not refer to millionths of an inch, nor does it refer to millimeters. It is what it is. So 1 mil of thickness, that's 1/1000th of an inch. And 1 square meter of area for 24 hours is 10 liters for hydrogen and 7 liters for helium at normal atmospheric temperature and pressure. 10 liters and 7 liters for 24 hours seems pretty high to my recollection, but maybe they had crappy plastic. So polyethylene is also easy to fabricate. It has an ultimate tensile strength of 1,900 pounds per square inch at room temperature, which is in a 15-foot balloon made out of 4 mil plastic, which represents a working pressure of about 2.3 inches of water. And let me just pull up a quick conversion here on my phone and see what 2.3 inches of water is in actual, like, modern day common units. So inches of water, 2.3, that would be 500 pascals or so. The tensile strength at the temperatures at which the balloon flies at high altitude may be more than three times the value quoted above. And the reason why they say that the tensile strength is going to be higher when it's flying is because plastics get stronger as they get colder. And this eventually translates into being so stiff and strong that they will shatter when they are flexed. So while they get stronger and stronger as they descend in temperature towards their brittle point, you can take advantage of it being stronger as long as you don't go too cold. So figure 1 shows the balloon flown successfully in Flight 26. So this is figure 1 from a real balloon flight. Another film they investigated is saran, which has 10 times the tensile strength of polyethylene. And yeah, that is the saran of saran wrap. That's pretty interesting. They tried it for balloons. 3 times the strength across the seams. Now, strength of the seams is pretty important in balloons under pressure because it's difficult to make good seams in plastic balloons. That's all for today. Be sure to like this video, share it with your friends, and subscribe to the channel.